Hello everyone, so I'm just doing this video today to help you build your understanding of R value. So as you're doing some research about thermal conductivity and heat being lost through walls and insulation, you may find that you are coming across something called R value. And we haven't learnt about this before. It's not kind of standard to teach in physics. Instead, what we tend to teach is something called K value. Now it so happens there's actually at least two other quantities that K value is related to, and I just want to show you how they're related. So we have K value, we have U value, we have C value, and we have our R value. Now just as a reminder, where does this K value come from? If I wanted to figure out how much heat is being lost through a wall, then I can use the thermal conductivity equation. And the thermal conductivity equation essentially says the Q over T, which is the same thing as the power being lost through the wall. So how many watts, how many joules per second. So I'm just going to use this power here rather than Q over T, but it's essentially the same thing. So the power, the heat loss through the walls, is equal to K multiplied by the area of the walls multiplied by delta T, where delta T is the temperature change from the inside compared to the outside. So, for example, let's suppose inside it's 20 degrees, then my T2 might be 20, and if it's outside at 0, then that would be T1 would be 0, and my delta T would be 20 degrees. And then you divide the whole thing by the thickness of the wall, so how thick the wall is, L. And that tells you loss. So K value is this number, this coefficient at the start right here. That's our K value. In terms of the units that you should see for it, well, if it's in SI units, then hopefully it will be in watts per area, so meter squared, per degree Celsius, and then multiplied by a thickness M. So when you reduce these units, it becomes watts per meter degrees Celsius to the minus 1. And sometimes rather than degrees Celsius here, you'll see Kelvin. So Kelvin to the minus 1. Now, I don't like to write it like this because it's kind of hiding the fact that you've got a meters which is cancelling out with a meter squared. You've got a length and an area here. But these are the units. Now, I want to relate this K value to what's called C value. C value is probably going to be the most useful thing if you want to calculate how much heat is being lost through a wall. So the C value takes into account how thick that wall is. So that way you can just get a number. So rather than it being per thickness, it just becomes per area. So if we want to go from K value to C value, what we actually need to do is divide by the thickness of the wall. So if the wall is 10 centimeters thick, you divide by your 10 centimeters. And so if we were to have a look, what is our C value? Well, our C value is essentially K divided by L here. That's essentially our C value. That's what this is here. And so that's going to tell us, it's going to have slightly different units. It's going to tell us how much energy is lost, so how many watts is lost per meter squared per degree Celsius. So if you've got a 1 meter squared of wall, it's how much heat will be lost through that every second for each degree difference between the wall outside and the wall inside. So if there's a 20 degree difference between the outside and the inside, you're going to lose heat 20 times faster than if there was only a 1 degree difference between the two. So if you want to go from C value back to K value, what you have to do is just multiply by the thickness of the wall. And that's how you can convert between those. Now you might find K values. When we do our calculations, we're mainly going to be trying to get C values. Those are really nice. Now the question is, how does R value fit into all of this? And the answer to that is that the R value is essentially 1 over the C value. So let's just go through and put some terminology on all of this. So K is known as our conductivity. So it's how conducting a particular material is. Now once you take the thickness into account, you're no longer looking at conductivity, but you're looking at what's called conductance. So that's how much heat will conduct through. So that's our C value. And our R value is actually our thermal resistance. And so it's the inverse of C, and you'll often find these R values quoted. Now if we just have a think for a minute, what makes a good C value and what makes a good K value? You want as little heat to conduct through a wall as possible. So you actually want a very low C value. So the lower the C value, the better insulating your wall is. Now for an R value, it's the opposite, it's the reciprocal. So that means the higher the R value, the better it is at insulating. And you might ask why are these R values used? And the answer is, well, they're very helpful to people who aren't so good at mathematics who want to figure out some insulation properties. So for example, if you're an insulation installer, you may not have a degree in physics and be particularly good at that. So you want something that's relatively easy to work with. Essentially, if you already have a wall and you know that it has an R value of 2, so let's suppose your wall originally has R value 2, and you want to add some insulation to it, and that insulation has also got an R value of 2. Then the total R value, you can just add these together. So the total R value will be 4. So that's really nice if you just want to be able to calculate the total R values quickly. You can just see, okay, if I add something extra, or if I had a wall, so let's suppose I originally had a wall, and it had an R value of 2. That's its thermal resistance. And then I add another one, which has an R value of 3, then you can just add it to get the total R value, and it will be an R value of 5. And so that's really nice. But the problem is, it's no good for actually calculating how much heat is lost. To be able to calculate the heat lost, we need to be able to convert our R values to C values. One other thing I thought I'd just mention at this stage is we just need to be really careful with our units. Sometimes rather than being R values, you'll see RSI values. If you see RSI, you know straight away this is good, because the SI stands for like Système International units. So they're going to be in the SI units that we always use in physics. That's really good. Sometimes though, R values can be quoted in imperial units. So the imperial units, rather than using energy in joules, they have what is called the BTU, which stands for British Thermal Units. If you see this and you need to convert it, just so you know, a British thermal unit is 1055 joules. So that's the conversion factor. But the problem is, if you see these British thermal units, you're probably going to be in Fahrenheit, and you might be using per square foot and this sort of thing. So you just need to be really careful with your units if you're looking up values online. Okay, I'm really keen to show you how we can actually use these R values. So let's have a quick shot. Let's imagine that we had a house, okay, and I might just quickly draw this house here. So top down, it can look like this rectangle here, okay? And then if I was to view it from the side, it might look like this rectangle here. So let's suppose that this is 7 meters long and this is 20 meters long from the top down view. And so this is my 7 meter long wall, and let's say that it's 2.5 meters high. I want to calculate the heat that's going to be lost by this house. Well, to do this, what I'm going to do is I'm actually going to say I only care about the heat in the interior of the house here. I don't actually care about the heat up in the roof here. For this calculation I'm going to do. If we just want to calculate how much heat is lost out of this area here, well, essentially there's 6 ways that the heat can be lost, because what we're looking at is essentially a long rectangular prism. So each of these faces, so there's a face here, 1, 2, then there's the top 3, and then if we were to kind of imagine, this is 3D, apologies, my 3D drawing isn't that good. So the top is number 3, this back wall is number 4, this back wall is number 5, and then there's the floor. Those are the 6 places where we can lose heat here. So another way of thinking about this is, where is all our power going? Where is all our heat going to be lost? Well, we can say that the total power loss, is going to be equal to the power loss through the walls, plus the power loss through the ceiling, the top bit, plus the power loss through the floor. And so if I was just to consider this back wall, so there's actually 4 walls to consider, but if I just consider this back wall here, how much heat am I going to lose through that? Let's suppose that has an R value of 2. So let's suppose the R value is equal to 2. Then the amount of heat that I'm going to lose here, it simply comes down to the power through the walls is going to be equal to, so you might remember my equation was K over L, A, delta T. But remember, K over L is actually just the U value. So what I can do here is say it's going to be my U value multiplied by A value multiplied by delta T. And my A here is my area. For this wall, the U value is just 1 over the R value. So it's just 1 over 2. And let's just remind ourselves, that's watts per meter squared per degree Celsius. Area of this wall is 2.5 meters by 7 meters. That's going to be in meters squared. And then we've got to figure out what's the temperature across this wall. So let's suppose we're going to assume that it's night time and it's 0 degrees outside because it's Canberra winter, and it's 20 degrees inside. So that makes my delta T 20 degrees Celsius. Now the question is, how quickly will I lose heat here? So this is for an R value of 2. Well, all I need to do is multiply these numbers together. So when I do this, my 2 here cancels out with my 2 here. So that becomes 175 watts. So that means every second I will lose 175 joules through this wall. Okay, so that's very useful for us to know. So if I want to counteract that heat loss, I'm going to have a 175 watt heater running. Now that's not very much of a heater. If I had 2 people in the room, they would actually warm up the room at the same rate that heat is lost. So that's not too bad. But now what I'd like to do is actually make this a slightly more complicated calculation here. You may notice that I had used a U value here rather than a C value. And you might have been thinking, what's going on with this U value? Well, the reason is there's actually something very similar to C value called U value. You can use the two interchangeably. However, C value only takes into account conductivity, whereas U value actually takes into account the loss due to thermal radiation and convection. And this would only make a difference if you've got radiation occurring. Now, through a wall, you're not going to have any radiation escaping, but through a window, you will. So for a wall, a C value and a U value are essentially going to be exactly the same. But for a window, you have to use the U value if you're going to have radiation passing through that window. So that's very important when the room is, say, warming up because there's the sun outside. Or if you just have the window without any curtains, then the heat can radiate straight through to the outside. Or alternatively, if you've got the window open and you're letting air in, that's going to make a huge difference to your U value because now you've got convection as well. So, if I was to add a window into that wall, and let's suppose it's a 2 meter window by a 2 meter window, I'm going to have to make a slight change to my calculation now. Because now I'm losing heat through the wall, just like before, but I'm also losing heat through the window. So let's see, how do I actually have to change my calculation here? Well, my power loss through this wall is now going to be essentially through the bricks plus through the windows. So I've got a separate term for each of those now. And so my power loss through the bricks is going to be, so the heat loss through the wall is going to be the C value or the U value for that wall, which was 1 over 2 because the R value is 2, multiplied by the area, multiplied by delta T. And then for my window, I'm going to use U value rather than C value because they could be significantly different here. A times delta T. Okay, so for the wall, C value is a half. The area is 7 meters by 2.5 meters, but now I've got this little chunk missing out of it, this 2 by 2 chunk. So that's minus 4 square meters. So all of that, that's in square meters, that's the units. So my wall is essentially slightly smaller than before because I've got this window. I'm still going to multiply by 20 degrees Celsius difference. Plus, now I've got to take into account my U value from the window. So I know from research that the U value for a standard non-double glazed window is about 6. And then if I multiply that by the area of the window, so in this case, it's going to be 2 meters squared, 2 meters by 2 meters, so that's going to be 4 meters squared. And then I'm multiplying by that temperature difference here. Now, when I do that calculation, I get 615 watts. Now, just to remind ourselves, before, when we didn't have the window, the power loss through the wall was 175. I'll just put that in brackets over here. So it was 175 watts. So if we were looking in this situation, what's the best way to prevent heat loss through the house? Do something about the windows or do something about the walls? We can see nearly all the heat loss here is being lost through that window. It's losing 600 watts, whereas the wall, the entire wall, was losing less than 200 watts. So this is a great way that I could justify, if I wanted to, that double glazing could actually be more important in this particular instance when I've got a very cold outside and a warm inside. So that could be far more important than putting better insulation in the walls. So hopefully now that you've watched this video, you have an understanding of how the K value that we've learnt about in class with conductivity relates to C value, and we also know how to convert R value into C value, and then we know that we can use either C value or U value to calculate the power that's lost through the wall, which tells us the amount of joules per second lost through the wall, and the formula is that the power is equal to either the C value or the U value multiplied by the area of the wall or ceiling or floor, whichever you choose, and multiplied by the temperature difference, delta T. So you can use that formula there, or you can use power equals UA delta T.